So we'll start from here where we left in the last class, the stresses in 3 dimension. So I have already told you what is triaxial stress, what is cylindrical stress, what is hydrostatic and spherical stresses. So if you see that our 3 dimensional plane is JKL. So if you the cosines of the plane from the three-dimensional plane, we will find three planes on three directions. So the plane is first area. First is the area KOL. Area KOL. Can you identify area KOL? The green area. KOL. Area KOL means the area hatching as green. Okay, that is the green area, the area KOL. What is that area of that KOL? KOL. What will be the area? This is the component of the main area A. We are taking A is the area of the three-dimensional place. We are taking, I'll show you something here. The components, how to calculation the components. If this is A, this is the cosine of the angle. And what will be the area at this plane, at this point, at this arma? That we simply write AL. If this is the area A, if this is the area A, this direction, and this is the cosine angle between and it will be L. So it will be, you can simply write down area at AOL. AOL is the AL, this is the X plane now. You see the KOL plane. KOL plane is nothing but simply the plane lying on the x-axis. So that will be along the x-axis. So that the area of the KOL we can simply write that is AL. Similarly, area JOK. JOK. You can say what is the area of that JOK. JOK is blue line area. The hatch starts blue. Who can say that is the area of JOK? Simply A. This is another component on y-axis. This is another component on y-axis. So that means we can simply write that is AM. Similarly, area that is what is left here JOL. JOL. But JOL is A and N. These are the area. These are the area of the different planes. So the components of stress sigma, that is the components of stress along each of the axes that we know, that is SS, SY and SZ, the component of stress along each axis. So you can say now the component is Sx, Sy, Sz. Then how can we represent this Sx, Sy and Sz in your cosine of angle? If these are the components, so sorry. If these are the components, so it is components means how to calculate the different components. Showing you here. Sorry, showing you here. Again, see, this is sigma. I want to find out the component of sigma in x-axis. So what will be the value of sigma in x-axis? If this is sigma, for example, if this is sigma at this direction, see this is sigma at this direction. If this is the sigma at this direction, so what will the component in this direction? If I am naming this as Sx, what is the component of sigma in this direction? Simply we can say sigma cos theta. If this is theta, we can say simply say Sx is equal to sigma cos theta. But we are already taken the cosine of angle, that is L. So we can simply say Sx is sigma L. So simply Sx is, now we can lie down, Sx is, just remembering this here. Sx is sigma L. Similarly, Sy is sigma M and Sz is sigma N. So this is all about the stresses in 3 dimensions, the component of the stress in 3 directions. So the question here arises is that what is the forces in particular x direction. If I am talking about the x direction, this direction only, this direction. If I am talking about the this direction, x direction, what is the component of different stresses in x directions? How can you calculate? So if you see here, we'll go for another sharing. You see, we have to go for the calculation of the stresses. Calculation of the forces in x direction. The summation of forces in x direction. So that is simply we can write summation of fx. Summation of fx. Just erasing this. Summation of fx. X direction. All the forces in x direction. So what are the amount of forces in x direction? What will the amount of forces? What is the component of forces in x direction? If you write here, if you see that figure previously, the previous page figure. So the summation of forces means the x direction of forces. So you can see shifting to here because of the availability of space. Sum of the forces in x direction is 0. This is the summation of forces in x direction. We can, this is the equation of writing, the method of writing some equations, equilibrium equations. So that the forces is the sigma area. When we're talking about the forces, then we are simply multiplying the area with the stress component. So we can calculate the force is stress is F by A. So F is sigma into A. So this is one force. Okay. Another x component force that we have sigma x L minus tau. I will show you in the last after writing the equation. Tau am, then tau zx an equals to 0. So see if these forces are there or not. We'll move to see these forces is there or not. Let's see. Let's see here. Screen is visible to you? Screen is visible to
Yes,
you?
sir.
Okay. So what are the stresses in x-axis? This is the x-axis position. This is the x-axis position. See this, I am circling it. We'll find it the 3D dimensional planes. The screen is visible though. Now the equation writing plane is visible. Which screen is visible?
Equation plan.
Equation page is visible. So that's all. I have to show you that. See this. The circling, the blue line circle. The blue circle. Now you can see these are the total stresses in the X plane. These are the total amount of stresses in X plane. Okay. So if these are the total stresses in the X plane, so in X plane we have, there is a component of sigma, the stress applied, the sigma, there is a component of sigma always, that we can write sigma is equal, the force is equal to sigma and stress into area is A and the component, cosine component is L. So that's why we are writing the first equation sigma in sigma, first equation, that is sigma AL, that we are writing first equation sigma AL is the first force. The second force is the sigma x, which is acting opposite to that the your normal stress. The sigma x, the component of force is, if the stress is sigma x, this is the force one, another force in x direction. and the stress in x direction. So what will the component of force in the x direction? So simply we will multiplying the area. Area is A, and in x direction the cosine angle is L. So that is again sigma x AL. Then what are the stresses, other stresses in x direction? There is a tau xy and another is tau zx. See this. One is tau xy and tau zx. Then the components of tau xy, if you calculating the forces due to the shear stresses tau xy and tau zx, then simply you can write tau xy. See the tau xy, area is the A, the cosine component is your M. Similarly, tau zx an. So these are the total number of forces in x direction. In x direction. Okay, in x direction. We are writing this in the manner. See the last setting. See, this is sorry, এটা কোন লিখে দিয়েছি? Okay. L minus tau xy am minus tau zx. So can you understand this?
Yes,
I
sir.
think in this equation where is the difficulty you find with stress or A or LMN? Where you find the difficulty? Just tell me. In this equation, in writing in this equation, where you will find the difficulty? Or in the plane, identifying the forces, stresses in the plane. Is it easy for you to identify the different stresses on the plane, or difficult for you? Hmm? Tell me accordingly, I will proceed. Okay. There is two conclusions.
Sir,
Okay. Tell me.
sir, sigma L is the total force.
Mm.
That's why we are
Sigma.
subtracting all this.
Sigma AL is the total force on the oblique plane or the three-dimensional plane. That's why we are not subtracting. We are these symbols, the negative symbols are coming because of the directions. When we are talking, if see, there is a force, this is a force, these are the, have you read about the component of forces, resolution of forces? If you see F1, F2, F3. If you are staying summation of fx is 0 for this case. So we can simply write down f1 cos theta minus f2 cos theta, or whatever, or anything else we are writing. We never be go for the positive. Why? Then the component of f1 is in this direction and the component of f2 is in this direction, the opposite direction. That's why the negative sign is there. The negative sign is due to the direction of the forces. The direction of the forces, not due to the this is total and we are subtracting. That is not. But the direction does not match with the direction of the total stress, that is sigma. The stress on the oblique plane. So in the stress is the normal stress is acting in different directions, and that these stresses are also in different directions. These are in different directions. So that's why we are going for the negative mark. So if you modify this equation, so simply here we can write here, see this, the above equation, sigma minus sigma x, making a common. So everywhere we have a, everywhere we have a. Now we can cancel the a. Now we can cancel the a. So we have now sigma minus sigma x into L minus tau xy m minus tau zx n is equal to 0. Now this equation reduces to in that format. Similarly, what we are doing here, we are calculating the summation of forces in x direction. Similarly, you can go for the summation of forces in y direction also. You can go for the summation of forces in y direction. If you go for the summation of forces in y direction, what will be the result here? The similar result we will find. So we'll find first the tau xy L plus sigma minus sigma y. Here there is no x because we are going for the y direction. So that is sigma minus sigma y, that is a minus tau zy. Then this is the forces in y directions. Now we can easily deduce the summation of forces in z direction also. Now you can easily deduce. Tell me, what is the summation of forces in z direction? What will be the forces in the similar calculations? The similar forces, three component of the stress. Everywhere there is the three components of the stresses will be there, and one component of the sigma will be there. So if we write here the summation of forces in z direction, so we have the equations like that: minus of tau xy L plus sorry, that is negative, there is no plus, minus of tau sorry xz, that is xy, no xy, that is only xz, xz minus tau zy m, and then minus plus of sigma minus sigma z equal to 0. Now it is three equations, that is equal to 0 na. This is equal to equation 1, this is equation 2, this is equation 2, and this is equation 3. These are the three equations. These three equations are obtained from the three-dimensional plane. Every plane we have what? Now every plane if you are going there are the three directional stresses. One direct stress, other two shear stresses. Every plane, one direct stress, and other two shear stresses. One direct stress and other two shear stresses. Everywhere the equation is very similar. There is no change. Once you have go for the calculation on one plane, the other planes are automatically be done there. So if you now I am clearing my whiteboard. So you find that in three equations, so there are three homogeneous linear equations. In terms of in all the equations you find the cosine components and L, M, N. If you see that see that equations, you will find the cosine components of L, M, N. The only non-trivial solution that can be obtained by setting the determinant of the coefficient of L, M, N equal to 0. That the three equations that we cannot solve these three equations because the L, M, N cannot be together 0. We cannot choose L, M, N equals to 0. That never be done. So that's why we'll go for the determinant form of element. Determinant form of element. So if you go for the determinant form of element, so first equation we have sigma minus sigma x. So I am writing this. See this equation carefully. Sigma minus sigma x. First there is sigma minus sigma x. Then there is tau minus tau xy. Then minus tau zx. Similarly, in the second equation, we have minus tau xy plus of sigma minus sigma x, sigma y. Okay, then we have tau zy. In the third equation, what we have? Minus tau xz minus of tau zx, zy, then plus of sigma minus sigma z. This is the equation, na? All are equal to 0. We are equating everything to 0. Yes, you are equating everything to 0. That is in terms of the equations are in terms of L, M, N. Everywhere we have this is here we have multiplied L. Here we have multiplication of L. Here the multiplication of M. And here the multiplication of N. That X will be continued throughout all the lines in this multiplied everywhere. The M is multiplied in that direction. The N is multiplied in everywhere in that direction. So we cannot choose element at a time 0. So that's why we are going for the determinant form of this equation by making. So we are going for the determinant form. Now see this. How beautifully the equation is made. This is the determinant of three-dimensional plane. That is equal to 0. So we can make determinant equals to 0. This is the first basic equation of the three-dimensional plane derived here. Okay. This is the first determinant form of the three-dimensional stresses. This is very much important. Okay. From here, from this determinant, if you read the mathematics, from the determinant, we have to go for the solutions. So here we have the three solutions. So here we have the three solutions. So we will go for what are the three solutions? We will go for it. First, solve the determinant. First, solve this determinant. If you are going for the solution of this determinant, what we will find? If we are going for the solution of the determinant, what we will find? Now I am just clearing this canvas. Here we will start writing the determinant format. That you have to calculate the determinant. That is a cubic equation. There are the cubic equation that we have to open the determinant and open the determinant, and we have to multiply each component to find out the solution of this. So after opening the determinant bracket, what is the solution we have here? See, that is the solution will be like that: sigma q minus sigma x plus sigma y plus sigma z, okay, into sigma square plus of sigma x sigma y plus sigma y into sigma z plus sigma x into sigma z into sigma z minus tau square xy minus tau square yz minus of tau square zx into sigma, then I'm changing my color, minus, that is sigma x, sigma y, sigma z plus 2 tau xy yz and zx, tau zx minus of sigma y, sigma x, tau square yz minus of sigma y, tau square zx minus of sigma z, tau square xy equal to 0. This is the solution. This is the solution what we will obtain from this determinant. So if you open the determinant is solved by opening the determinant bracket, that every corner is first multiplied, then each component will be multiplied. By multiplying this, we will find this will be the equation. That is a cubic equation. See here, there is a cubic equation. There is a cube. So it is a cubic equation. If there is a cubic equation, so we have here go for you have three components. If there is a quadratic equation, in mathematics there is a quadratic equation. Quadratic equation means there is two solutions of that equation, that is 1 and 2. If there is a cubic equation, then we have three solutions of this equation. So that is sigma 1, sigma 2 and sigma 3. These are the principal stresses. From this equation, we can calculate the three principal stresses: sigma 1, sigma 2, and sigma 3 from the solutions. So, to determine direction, there is the three stresses. These are the principal stresses. These are the three principal stresses which can be calculated from this equation. From these equations, here we will calculate the stresses. We can also calculate the directions of these principal stresses. Direction of the principal stresses, we can go for the direction of the principal stresses. It is necessary to substitute sigma 1, sigma 2 in each turn into the three equations. The resulting equation must be solved simultaneously for L, M, and N with the help of auxiliary relationship. L square plus M square plus N square is equal to 1. So, when you go for the solution of this equation, now here there is an assumption that L square plus M square plus N square is equal to 1. When taking these assumptions, this is assumption. L square plus M square plus N square is equal to 1. This is assumption. This is assumption, we are taking this. So, here we will find the three combination of stress components. This is the most important equation. This equation is the most important equation from your subject point of view. This equation, most important equation. Okay, so this is here. Before that, we have three equations. 1, 2, 3, and this is the equation number 4. I am writing here because there is no space here, so that's why I am writing here. This is equation number 4. This is equation number 4. So in equation number 4, we have there are three combination of different stresses and the coefficient of the cubic equations. Three different combination and coefficients of the cubic equation. Since the values of these coefficients determine the principal stresses, they obviously do not vary with the changes in coordinate axes. So there is the chance of the varying with the coordinate axis is less. Therefore, any invariant coefficients. So from this equation, we will find some invariant coefficients. The direction, the stresses with the direction cannot be changed. That means which component, the component which cannot be changed, that is called as your invariant components. As I have already told you, the components, the components which does not change, that are the invariants. So what is the invariant here? I have already told you that the theory that the stresses with the direction cannot be changed. So that means we have the first invariant like your, see I am marking it, first invariant. That is called as I1. I for invariant. That is called I1. Sorry, I1. This is first invariant. First invariant means I1 is sigma x plus sigma y and sigma z. That is never be changed. That is always constant. That means if x is changed, the proportionate amount of y and z will be changed. So if you say sigma x plus sigma, the different stress components, all the three components will be, by adding all the three components, they are 100 MPa. The stress in MPa, 100 MPa. So in the next moment, we are saying that sigma x is changed to 50 MPa. So that means the sigma y and sigma z, summation of sigma y and sigma z will be of the 50 MPa. If you change sigma x is 30 MPa, then the summation of sigma y and sigma z is 70 MPa. So that means these are the invariants. The summation cannot be changed. This is the first invariant what we have obtained here. The second invariant is here. The second invariant, sorry, the second invariant is here. And this is the second invariant, that is written as I2. This is the second invariant. Okay, this is the second invariant, and there is also a third invariant, that is here. This is the third invariant. This total component is the third invariant, I3. These are the invariant of stresses, three-dimensional stresses. These are the invariant of three-dimensional stresses. So while writing the three-dimensional stresses in the separate format here, this is the determinant. I am going to erase this format. So I am writing the invariants now here. The first invariant I1 is just sigma x, sigma y plus sigma z. This is first invariant. So second invariant is I2, that is your sigma x into sigma y plus sigma y into sigma z minus plus sigma x into sigma z minus of tau square xy minus of tau square yz minus of tau square zx. Okay, this is second invariant, and third invariant is I3. I3 is a little bit lengthy, that is sigma x, sigma y, and sigma z plus 2 tau xy, tau yz, tau zx. So there is less than 1 minute and it will be stopped. Meeting will be closed. After that, you have to re-log in here. Okay. If the invariant will be completed, no need to be re-log in. If invariant will not completed, then you have to re-log in here. I am just writing these equations. So x minus of sigma x tau square yz minus of sigma y tau square xy xz minus of sigma z tau square yx. So these are the invariant of stresses. So